Good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. In our last two classes we have been discussed on the topic of one-dimensional infinitely rigid box or it is infinitely deep potential well. And from our discussion we have been found that outside the box the particle does not exist. That means uh, the wave function beyond x is equal to 0 or beyond x is equal to L will be 0. That we have been found from our discussion. So here I will suggest to all of you that before you have to watch today's video, at least you have to go through the last two videos. Okay, so because today's video has the link somewhat with the last two videos. Okay, so all the derivations we have been done and we found that the wave functions after solving that one we found the general wave function will be in the form of sin x equal to b sin n pi x by L, which will be called as the Eigen function, and from that also we derived that energy eigenvalues and how they are separated with each other, or what will the difference between the two energy level and how the difference between the two energy level value is going to be increased, and at the higher energy level how and why it has to show the quasi continuous of distribution of energy level. That we have been also discussed, and we discussed about linear dimension of the box, effect of linear dimension of the box on the quantization of energy, and energy eigen functions. So eigen functions we found by considering the normalization condition of this wave function, and we found that will be the 2 by L root over sin n pi x by L. So all the we have been discussed in our last two videos. You have to go through that two videos, and also we discussed the each and every energy states and their corresponding eigen functions. So this is the first state and its corresponding eigen function, second state corresponding eigen function, like that we have been derived, and this is the plot of wave functions for different states, and this is the plot of probability distribution for each state. Okay, so if you have to go through those two videos, then you will be clear on these topics whatever I'm saying, that these the previous ones. So then we have been discussed about orthogonality of wave function. So how the two wave functions of two different eigen functions or two different wave function of the two different stationary states, they are behaves mutually orthogonal with each other. That also we have been proved. Then we have to go for the eigenvalue of momentum. So before that we have to discuss about the energy and momentum eigenvalue equations. Momentum and energy eigenvalue equation. So we know that eigenvalue equation in the generalized form. In the generalized form, we know the eigenvalue equation will be like this. This is the, suppose this will be the q, and this will be the psi q. Suppose it will be q and psi q. That means whenever a operator is going to be operates over a wave function, then it will be transformed, or it will give a eigenvalue, and it will be keep the same wave function. Then it will be called as the eigenvalue equation. Suppose q cap operates over psi q and it is given some value, constant value, but this is changed to suppose psi n. Here these two wave functions will be not same after operated by this operator. So this equation could not be called as the eigenvalue equation. So we need the eigenvalue function, eigen functions for the operator of energy and momentum. So energy means Hamiltonian. So for the Hamiltonian we need the energy eigenfunction, and for the momentum we need the momentum eigenfunction. Then we can define the so-called eigenvalue equations for energy and momentum. So that things we are going to be discuss over here. See, the particle, the situations whatever we have been taken for this case is the particle moving freely along x-axis with linear momentum p, means only px component it has. Particle has only px component, right? And the kinetic energy will be px square by 2m. So as particle moving freely, the potential on the particle will be zero, or hence we can say the potential energy possessed by that particle will be zero. Hence the total energy of the particle will be kinetic energy only, that it will be p square by 2m. Hence corresponding Hamiltonian operator is, means it is total energy operator, Hamiltonian operator, or we can say it is total energy operator. We know these things. Okay, total energy operator or Hamiltonian operator will be h cap will be px cap square by 2m, and we can found that h cap and px cap both are commute with each other. Okay, how it has to be commute? Here I have been written with you can write, you can pause the video and you can write. Sometimes it is asked in your exam that prove that h cap px cap will be equal to 0, means they both are commute with each other. Okay, for a free particle. So for a free particle, total energy will be nothing but kinetic energy, potential energy 0, E equal to px square by 2m, or h cap is nothing but px cap square by 2m. Okay, so now px cap square 2m. So instead of h cap, I can write px cap square by 2m, px cap. So 1 by 2m can be taken outside. It will be px cap square into p x cap, and 1 by 2m I can write it will be px cap into px cap comma px cap. So by using the properties of commutation properties, you can follow our previous video. We can write 1 by 2m will be here, this px will be go this side, px cap plus another px here can be moved this side, it will be px cap px cap. So we know that the commutation of a operator with itself can be done, means one operator commute with itself. So any operator, suppose a cap is operator, a cap operator always commute with itself. Okay, will be 0 always. That means a cap minus a cap will be 0. It is obvious. So hence we found h cap px cap commutation between h cap px cap will be 0. So since h cap px cap are commute with each other, they have a simultaneous set of eigenfunction. So if we have two operators and they are commuting with each other, or they are compatible with each other, then they have a simultaneous set of eigenfunction, means we can found a wave function or eigenfunction will be common for this and common for this. So this will be also a one type of theorem, oftenly it is asking in your exam. So that I have been written over here. You have to pause your video and you can write in your extra page. So these two things we have been interacted here, and I have been proved here for your better understanding. So these two questions you can write some other place of your note, but you very much useful, this one and this one. Basically this one is very much important. Oftenly asking in your question up to 3 to 4 marks. Okay, so here prove that if two operators a cap and b cap commute with each other, they have a simultaneous set of eigenfunctions. So whatever we have been written in the sentence here, so that's proof here I am doing. You just watch it, and by pause the video you can write also. It is given that a cap and b cap commute with each other. That means a cap b cap with square bracket will be 0, or a cap b cap minus b cap a cap will be equal to 0, or a cap b cap equal to b cap a cap. Let us consider psi k be one complete set of eigenfunctions for the operator a. Let psi k is the eigenfunction of the operator a. So here a operates over this function. It will be induce a eigenvalue, and same eigenfunction will same wave function will be present at the right hand side. So this will be nothing but the so called eigenvalue equation for the operator this one, because this psi k is a eigenfunction of the operator a cap. Okay, so now then I have to operate b cap over here. So b cap a cap psi cap will be equal to here a cap psi cap is nothing but a cap psi cap is nothing but a k psi k. So b cap will be here. So b cap will be here. This will be a k psi k. So a k is a eigenvalue, will be constant, can be taken outside and can be written as in this form b cap psi k. Okay. Or we know that as both the operators are commute with each other, a cap b cap equal to b cap a cap. So instead of b cap a cap, I can write a cap b cap. Okay, a cap b cap psi. Instead of this one, I have been written over here a cap b cap sorry, psi k will be equal to this much, will be equal to this much, right? Will be equal to this much. So here I can write in this form that a cap in bracket b cap psi cap is equal to a k b cap psi k. Okay, so if you can watch this equation number 1 carefully, what we can found, this equation will be give a smell of eigenvalue equation. That means this equation represents a eigenvalue equation in which this b cap psi cap will be a eigenfunction of the operator a cap having the eigenvalue is a k. So this equation 1 represents an eigenvalue equation. It implies that b cap psi k is an eigenfunction of a cap belongs to the eigenvalue ak. Okay, so but b cap psi k will be nothing but some constant psi k. Okay, so if b cap will be the operates and psi k is going to be operates over psi k, it will be produce the result as constant and psi k, or it will be it can be written as bk psi k, right? So hence we can say that psi k means here k can be 1 2 3 like that. Okay, so psi k is the set of eigenfunctions for both a cap and b cap. Proved. So this is the method in which we have been proved that if a cap b cap commutes with each other, then they have simultaneous set of eigenfunctions. Okay, so I suggest to all of you, you have to write these two informations or two questions in your note, which will help in your exam. So now here we found that since h cap p x cap are commute with each other, they have a simultaneous set of eigenfunctions. let psi x will be the eigenfunctions of h cap and px cap. Okay, here in our discussion, here we have been considered psi x will be the eigenfunctions for both h cap and px cap. Now this psi x we are going to be search what will be. Okay, the energy eigenvalue equation can be written as, if psi x will be the eigenfunction, the energy eigenvalue equation can be written as h cap psi x will be equal to E psi x, or h cap is nothing but px square by 2m, psi x will be equal to E psi x. Here psi x is the function of x. Okay, so and h cross square minus, so p square px square will be nothing but how much? It will be minus h cross square into del square by del x square. Okay, or px square by 2m will be operator will be there. So it will be minus h cross square by 2m del square psi x by del x square will be E psi x. Okay, so this can be written as del square psi x by del x square plus 2m E by h cross square psi x will be equal to 0. So this will be the this can be written as in this form, del square psi x by del x square plus k square psi x will be equal to 0. Let it is equation number 2. Now the momentum eigenvalue equation is px cap psi x will be equal to px momentum value, or we can say the eigenvalue of the momentum operator and psi x. Okay, so this will be the so called eigenvalue equation for the momentum. This will be called as the eigenvalue equation for the energy, because here we are considered that psi x will be the eigenfunction for both energy and momentum. So here you can see this one and this one is the so called your eigenvalue equations. Now we have to consider psi x in such a way that it has to satisfy for both the equation 1 and equation 2. See, this all are equation number 1 we can say. Okay, so we have to consider a psi, or we have to search a psi in such a way that it will be satisfy both equation number 1 and equation number 3. So what is that psi that we are going to be search? See, now consider for that consider the equation number 2. Equation number 2 is what? Del square psi x by del x square plus k square psi x will be equal to 0. The two roots of these equations will be how much? Plus ik and minus ik. Hence the two solutions also can be possible. That means these two roots we can found from this equation, and we can say that these two solutions can be possible for this equation. The two solutions will be the two solutions are a e to the plus ikx, let it is equation number 4a, and another solution can be b e to the power minus ikx, let it is equation number 4b. Okay, 4b. Or linear combinations of two solutions will be also a solution if Wronskian is not equal to 0. So here you can found that Wronskian is nothing but your a e to the power ikx and a b e to the power minus ikx, and this will derivative of this one, so it will ik a e to the ikx, the minus ik b e to the ikx. That means this determinant if not equal to 0, you can see that the determinant is not equal to 0 itself. See, and this will be, the determinant will be how much? The determinant will be a into b into minus ik. If I am going to multiply this will be e to the ikx into e to the minus ikx will be e to the 0, leave it minus this will be a into b plus ik, right? So it will be how much? Minus 2ik into ab, which is not equal to 0. So if we know that if Wronskian will be not equal to 0, then both the solutions are linearly independent, and we can take the linear combination of that two solutions also be called as the solution of the differential equation. So here Wronskian is not equal to 0, so hence the linear combinations of two solutions will be a solution of the equation number 2, that will be psi x will be equal to a e to the plus ikx plus b into e to the minus ikx. Let it is equation number 4c. So here from the equation number 2, from the equation number 2, differential equation number 2, this is equation number 2, we found that three different possible solutions, this one, this one and this one. Okay, so what we have to choose, or which solution we have to consider, that it will be the eigenfunction of the energy and eigenfunction of the momentum, that we have to check. Now now to verify which solution, now to verify which solution means 4a or 4b or 4c will be the simultaneous eigenfunction for energy and momentum. First we have to consider 4a solution that is psi x equal to a to the plus ikx. For energy we have to consider. For energy, suppose I am going to we know that eigenvalue equation is h cap psi x will be equal to how much? Px cap square by 2m psi x. So px cap square by 2m will be written as minus h cross square by 2m del square by del x square, and psi x we have been considered as a e to the plus ikx. So a e to the plus ikx. So we can found that minus h cross square by 2m. So ik square a e to the plus ikx, that we found h cross square k square by 2m psi, or this is the dimension of E. We know that p square by 2m is nothing but E, and p is nothing but h cross k, right? So here h cross square k square by 2m is the dimension of the energy. So what we found? We found that h cap psi x is equal to E psi. So hence this one is considered as, hence psi x equal to a e to the plus ikx is considered as energy eigenfunction. Okay, now for the momentum we are going to be check. So px cap psi x will be written as px cap, the operator value is nothing but I minus I h cross del by del x, momentum operator, a e to the plus ikx. So here it will be minus I h cross ik, derivative of this one, a e to the plus ikx will be equal to h cross k psi x. So here px cap psi x we found h cross k psi x. So h cross k is nothing but the dimension of the momentum. So this is the momentum eigenvalue. So we can say that this will be this one. See, px cap psi x is equal to px psi x. So it is satisfied the so-called eigenvalue equation. So hence this psi x, that means a e to the plus ikx, will be considered as momentum eigenfunction. So here psi x or the in the equation number 4a, that is a e to the plus ikx, is a simultaneous wave function for energy and momentum. Now we have to check for the 4b equation, that is b into e to the power minus ikx. So similarly you can check that h cap psi x will be equal to, you can pause the video and you can write. I am not going to explain here each step because it is very easy, only double derivative you have to take. You have to pause the video and you can write. So here h cap psi we can found h cross square k square by 2m b e to the power ikx, that means psi x. So it is satisfied the eigenvalue equation, that means h cap psi x will be equal to e cap psi x. So hence psi x equal to b e to the power minus ikx will be considered as energy eigenfunction, because this psi x satisfies the eigenvalue equation. Okay, now for the momentum we have to check, is it acceptable for the momentum eigenfunction. Let's see. So this will be, you can pause the video. So here we can say, we can operate momentum operator psi x. So we can found at last that plus I square h cross b e to the minus I k x. Okay, that means minus h cross k b e to the minus I k x, or we can, this is also minus h cross k is also the dimension. See, only negative sign indicates here. For plus I k x we found h cross k. For here minus e to the minus I k x we found minus h cross k. That means the particle, whenever it is moving this side, along this side, x-axis along this side, positive direction, the momentum will be h cross. When it is moving this side, negative, along negative x-axis direction, it will be minus h cross, because particle in one dimension motion is to and fro motion. So this side, whenever it is moving towards this side, it will be h cross k. Towards this side, it will be minus h cross k. So this negative sign indicates the direction. So but this will be the dimension of the momentum. Hence psi x will be equal to b e to the I k x will be considered as momentum eigenfunction, and this psi x also you considered as by considering this psi x, we can write p x cap psi will be equal to p psi x. That means the eigenvalue equation can be satisfied by considering this wave function for the momentum. Here I written a small mistake. This will be h cap psi will be equal to e psi, because this is the eigenvalue, right? So please be corrected. So we found that both equation e to the power, so here we found that both 4a and 4b, that means a e to the plus I k x and b e to the minus I k x, both are considered as energy eigenfunction and momentum eigenfunction. Now we have to check for this one. What we are going to get the result. Let's see. Now the equation is 4c. The equation in 4c, that is psi x is equal to a e to the I k x plus b e to the minus I k x. So this function, this solution will be the eigenfunction for both or not, that we are going to be check. So we have to apply the total energy operator over this one. Then what we are going to get? See, this is nothing but px cap square by 2m and psi x value I have written over here. So this is nothing but minus h cross square by 2m del square by del x square, and this one. So simple double derivative I have been taken, and I got this one. Then you just pause the video and you have to write the steps. So then this will be I square k square can be taken outside. This will be minus h cross square by 2m into I square k square will be this one. So this will be equal to h cross square k square by 2m and this one. That means this is the dimension of the energy, or we can say this will be the eigenvalue of the energy, and the same wave function at last we found. That means we can say h cap psi x will be equal to e psi. That means we can say this one. That means the present wave function, whatever we have been taken for energy, this will be called as energy eigenfunction, and corresponding energy corresponding eigenvalue equation is this one. Okay, so this psi x will be called as energy eigenfunction, and for the energy operator, total energy operator, this is the energy eigenvalue, and this whole equation will be called as energy eigenvalue equation. Okay, or eigenvalue equation, only eigenvalue equation, or you can say energy eigenvalue equation. Okay, so this psi x will be considered as energy eigenfunction. Okay, now is it acceptable, this psi x will be acceptable for momentum eigenfunction? Yes or no, that we have to check. So it will be px cap. For that, px cap psi x, px cap is nothing but minus IH cross del by del x will be this much, minus IH cross, and this is a simple derivative of this one. It will be ik a e to the ikx plus minus ik into b e to the minus ikx, and it will be minus IH cross, and this ik can be taken outside. This will be a e to the ikx minus b, simple steps. So at last we found that h cross k, but the wave function is not same with the initial. That means px cap psi x is not equal to h cross k. H cross k is the dimension of the momentum, but is not this one. This will be this psi x is not same of this one. It means left hand side is not equal to right hand side. Right hand side, because this psi x is not equal to this psi x. So that psi x, that equal to a e to the ikx plus b e to the minus ikx will be not considered as momentum eigenfunction. So what we found in our discussion, that so from the above discussion what we found, psi x equal to a e to the power ikx and b e to the power minus ikx are considered as the energy eigenfunction and momentum eigenfunction. Both for both means this and this are considered as energy eigenfunction. Here you can just language change, as well as momentum eigenfunction. So the corresponding eigenvalue equations are h cap psi x equal to e psi x, or we can write h cap a e to the ikx will be equal to e. This is the energy eigenvalue, a e to the ikx. For the momentum, px cap psi x will be equal to, this is momentum eigenvalue psi x, or px cap, this psi x we have been taken as a e to the ikx, will be equal to p a e to the ikx, and h cap b e to the minus ikx will be equal to e b e to the ikx. We are considering this wave function, right? And px cap b e to the minus ikx will be equal to p into b e to the ikx. Okay, so these are called as the eigenvalue equation of for energy, this one, energy and momentum. So but this one is not considered as this one is considered as only energy eigenfunction, not for the momentum eigenfunction. That is h cap psi will be equal to e psi if we have to consider this one. This could not be considered as momentum eigenfunction. So in short, I have been written in the note that momentum eigenfunction will be considered as either a e to the ikx or b e to the minus ikx. Corresponding eigenvalues are what? H cross k plus h cross k or minus h cross k. Energy eigenfunction can be considered as a e to the ikx or b e to the minus ikx, or a e to the ikx, means linear combination also can be considered as energy eigenfunction. That is a e to the ikx plus b e to the ikx, and the corresponding eigenvalue is nothing but h cross square k square by 2m. So another small things I have been written over here that you have to write, that eigenvalue of the momentum. Already eigenvalue we found that either it will be plus h cross k or minus h cross k. So the similar type of things also we have been derived in other way, that we know that p square by 2m will be nothing but kinetic energy for this free particle, and this is nothing but E. And if we have to consider E for each energy level corresponding momentum Suppose this is in generalized, because we know that for one dimensional potential well problem, whatever we have been discussed, it has a different discrete energy level. That means if particularly here, what will be the momentum or what will be the velocity, if it will go to the second excited state, the momentum or the velocity will be changed. Third, it will be changed its velocity. So as the energy states are discrete for this case, so only for that corresponding momentum also discrete. So here we can write Pn square by 2m will be equal to En, and Pn square, P subscript n will be equal to En into 2m, will be can be written as n square pi square h cross square by L square. So Pn will be plus or minus n pi h cross by L. So P1 means momentum at first state. Sorry. Here Pn equal to plus or minus n pi h cross by L, and if we have to consider P1 will be equal to plus or minus pi h cross by L. Okay. And P2, that P2 will be equal to plus or minus 2 pi h cross by L. P3 will be equal to plus or minus 3 pi h cross by L. That means whenever the particle will be at the first excited state, this is the first excited state, and it is moving towards this direction, this value, the value of the momentum will be plus h cross pi h cross by L. If it is moving this side will be equal to minus pi h cross by L. And if the particle will be at this state, second excited state, and is moving towards this side, then its momentum will be plus 2 pi h cross by L, and if it is moving towards left, then it will be minus 2 pi h cross by L. See, this one also dimension of h cross k. We know that in general P is nothing but h cross k, right? So here k, here k is nothing but 2 pi by lambda, 2 pi by lambda, and h cross. So if you are going to compare this one with this one, you can find h cross, this is pi is here, and divided lambda, or you can say the so called length. So this dimension is same with this dimension, but for this particular situation, particular dynamics, that means on this state, first state, the value of the momentum will be plus h pi h cross by L, or h cross pi by L towards the right, and towards left it will be negative. And these values can be represented in this form, means with the state wise form. That means it is zero momentum. That means if the particle is inside this one dimensional box, that means it has some momentum. At the ground state or at the minimum energy state, it has either plus pi h cross by L or minus pi h cross by L. That means if the particle will be at ground state, either it is moving this side or it is moving this side, means this particle is always in to and fro motion. To and fro motion means it is tends to moving towards right or towards left. And this scenario also we can found with other excited states, but with different momentums, and the momentums are for the second state, this is for n is equal to 1, and this is for n is equal to 1, this is for n is equal to 2, this is for n is equal to 2, and this like that. So for n equal to or second excited state, the momentum either it will be plus 2 pi h cross by L or minus 2 pi h cross by L. That means it is moving towards right with this value or left this value. So this is all about your one dimensional potential, deep potential well, or one dimensional infinitely rigid box. That means we have been discussed all the contents regarding this topic. So you can say that it is very long, and what we have to do for the exam, I can suggest that in your exam they are going to be asked the particular questions. So on the base of that you have to write in your exam. Means they are not going to be asked all the things you have to derive. They are going to be asked for the particular content you have to derive for this problem. Okay, so what is the question is asked in your question, that is the matter. On the base of that you have to write those things. Suppose I am going to give I can give you one example. Suppose it has asked that one dimensional box, and you have to find out the energy energy eigenvalue, or it's a normalized wave function. So these things you have to write, but in the synchronized manner you have to write. Okay, synchronized manner you have to write. And this outside the box it is zero, so not to be right. No need. So these things you have to write. And up to this much. And doing the normalization, you found this one. Doing the normalization, you found this one. Okay, and maybe they asked you about energy states of different, so you have to write this one. These things. Okay, so, and these two graphs also you have to write. You have to write these two graphs. This one probability location, no need to write. If you have to write, if you write, no problem. And here in case of probability locations, step by step I derived, no need to derive the step by step from this equation. This is the conditions we found, and these are the variations we can found in each state. That's it. Means maximum 4 pages, maximum 4 pages you can write your question if it is asked in a question. Suppose orthogonality of the wave function, they asked 3 marks, only you have to write this one, right? And they asked about this one, energy and momentum eigenvalue equations, so you have to write this one. So first you have to judge that what is the question asked in your exam. On the base of that you have to write in the exam. So no need to write all the things, because it is so too long. Here we only discussed all the contents regarding one dimensional box, and I hope you understood. And again I suggest that you go through these three videos of this topic. Wherever you have doubt, you can ask me. Okay, so thank you so much for watching this video. Thank you.